Chapter 2, Initial ArduPilot Configuration. In this chapter, we are going to be going through all the steps to configure the ArduCopter software on a new drone for the very first time. This assumes that your ArduCopter drone is already configured in hardware, that is, it's all wired up correctly, and we're going to be going through all the steps to make sure that your flight controller can communicate with all of the drone peripherals, to make sure that it can control correctly all of the motors on the drone. We're going to be going through the accelerometer and compass calibrations to make sure that they are aligned correctly, and we're going to be looking at compass interference to make sure that your compass is not being affected by electrical noise from the motor's ESCs or battery leads. After we've done all that, we're going to be setting up the logging settings to make sure that when we do our first test flights, we are capturing all the data that we are going to need. There's a link down in the video description to where you can download Mission Planner, but you should be aware that there is a bug with the latest version of Mission Planner as of the time of this recording, which is 1.3.82. And that bug basically makes it impossible to download logs from the drone over USB. It's just incredibly slow. It's basically unusable. So for what we're going to be doing, we need to be able to download logs. So you're going to want to use either version 1.3.81, so the previous version, or you can apply the beta updates from the help page. If you go to the help page in Mission Planner and then click check for beta updates, that will apply the updates, one of which fixes this logging bug. The first parameters that you're going to want to set up are the frame class and frame type for your drone. You'll find this in Mission Planner, Setup tab, Mandatory Hardware, and Frame Type menu, and you should see a page that looks something like this. There are a whole bunch of different frame classes that are supported by ArduCopter, and also a whole bunch of frame types. We're going to start by selecting the frame class, and this is based primarily on the number of motors that you have on your drone. If you have 4 motors, that's going to be a quadcopter, and you're going to be using this frame class. If you have 6 motors, that's a hexacopter. And if you have 8 motors, that's going to be an octocopter. There are also classes for coaxial setups. So if you have 8 motors and they are 4 sets of 2 coaxial motors, so you have a coaxial octocopter, then this is the frame class for you, the coaxial octo. Similarly, if you have 6 motors in a coaxial tricopter setup, then you can select this one. A traditional heli is going to use this setting here, so that's with a single main rotor and a tail rotor. And then this final one is for a tricopter with a servo actuated tilting tail for yaw control. This is not all that common nowadays, but if you do have a tricopter with a tilting tail, then this is what you're going to be using. Once you've selected the correct frame class, it's then time to move on to frame type. There are, again, a whole bunch of different frame types in this section here. A plus type frame is where you have a motor directly in front of the direction of travel. So if you have a quadcopter with a motor directly in front of the direction of travel, then you can set the plus type. And similarly for a hexa, an octo, or a heli, you're going to choose the plus type. If instead you have a more common X type layout, where you have 2 motors kind of either side of the direction of travel, and then additional motors spaced symmetrically around, then you're going to choose the X type. And if you're going to choose something like the Y6A for the coaxial hexacopter layout, then that's also the same. You're going to choose this setting here. You can also use this setting for coaxial octocopter and for the tricopter with the tilt tail. A V-type layout is the same as the X, but with a V-type layout, you have the front motors wider spaced than the rear motors. And this is very typical for camera drones. So if you do have a camera drone, you might choose a V-type layout if you have wider spaced front motors. There's also an option for a V-tail. This is where you have the 2 rear tail motors angled so that they provide significant yaw authority. In this mode, ArduCopter won't use the front motors for yaw control at all. It'll just use the rear V-tail motors to control the yaw. Again, this is not a very common layout. There is also an A-type tail, which is the same as a V, but with the motors angled the other way. You can find that in the full parameter list if you want to use that setting. An H frame, again, not very common. The only difference between an H and an X is that the direction of the spin of the motors is different. And you also have a Y6B, which is the same as the Y6A, but with all of the motors spinning in the opposite direction. So if for some reason you want to use a reversed rotation direction for all of the motors, then you can select Y6B for that. There are additional options for frame type and frame class, including options with more than 8 motors. So if you have a drone with a particularly large number of motors, you can find that in Mission Planner, Config tab, Full Parameter List, and then you just need to search for frame underscore, and then you'll see 2 options for frame class and frame type, which cover all of the options that are available on this page, and also some extra ones that are less commonly used. Next, we're going to do the initial tune parameters. And here we're going to set the prop size in inches, the battery cell count. I'm using a 6S pack, so it's going to be 6 for me, and the fully charged cell voltage and fully discharged cell voltage. You can either set these manually, or you can just select the battery chemistry from this drop down, and then it will populate them automatically. You're also going to want to tick the Add Suggested Settings for 4.0 and up, which includes settings for battery failsafe and also sets fences, which is like an altitude limit and things like that. If you don't want to set battery failsafe and altitude limit, then just leave that box unticked and hit Calculate Initial Parameters, and then write those parameters onto the ArduPilot firmware. The next step is to set up your board orientation. Now, you'll only need to change this if you're using your board in an orientation that's different to the orientation that the manufacturer expects, the manufacturer default. If you need to change it, you can go into the Config tab in Mission Planner, go into the Full Parameter List, and search. The search box is on the right-hand side. Search for AHRS_orientation. You should be able to find this parameter, and then you can set it to the correct value based on how your board is orientated. For example, Maytech expects that the H7A3 is going to be set up so that all of the components are facing downwards. Now, in my case, that would mean that all the components are right next to the ESC, and I'm worried about interference having all the components right next to the ESC. So I'm going to be flipping the board over. I'm going to be flipping the board 180 degrees on the roll axis. So I'm setting my board orientation to number 8, which is 180 degrees roll, and that's correct for me. If you're using your board in the standard orientation, then you don't need to make any changes, just leave it set to 0. But obviously, if you've got a different board orientation, this is where you set it up. Once the board orientation is set correctly, it's time to move on to calibrating the accelerometer. And to do that, we're going to go into the Setup tab, Mandatory Hardware, Accel Calibration, it's just here, and you can see we have 3 options. We're going to do the Calibrate Accelerometer first, then we're going to reboot the flight controller, and then finally we're going to do the Calibrate Level. To calibrate the accelerometer, you just need to follow the instructions on the screen. So you click Calibrate Accel, and it will tell you to hold the drone level. Just hold the drone approximately level, keep it nice and still, and then click Done. Then you'll be told to put the drone on its left side. And again, when you've done that, hold the drone nice and steady and click Done. You'll then be asked to do the right side. Again, click Done. Then nose down, click Done. Nose up, click Done. And finally, hold the drone on its back, nice and level, and click Done. Once you've calibrated the accelerometer, then you're going to be calibrating the level of the drone. Here, you want to take the drone and put it on a nice flat bench, like this. Leave it nice and still, step away from it, and then click Calibrate Level. That will set up the true level for the drone, and that's what's going to be used in the stabilize mode to keep everything nice and still. So it really does help to make sure that that level is really accurate. Once you've calibrated the accelerometer and calibrated the level, you don't need to do anything else. So typically you won't need to use the simple Accel Cal at all. That's for much larger drones that you simply can't do the normal calibration with. Once the accelerometer is calibrated, we can move on to the compass. And here we're going to just go down to the onboard mag calibration and hit start. Now, the best way to do a compass calibration is actually very similar to the way we did the accelerometer calibration. And it also does help here to have a nice long USB cable. So to start with, we're going to take the drone and hold it level and then do a full 360-degree rotation, nice and slowly to the left. And then a full 360-degree rotation, nice and slowly to the right. Then we're going to put the drone on its left edge and do another 360-degree rotation to the left, nice and slow, and then back to the right again. Now put the drone on its right-hand side and do exactly the same thing. So rotate to the left and rotate back to the right. Now put the drone nose down and again rotate left 360 degrees and then right 360 degrees. You can probably see where this is going. Now we go nose up and again 360 degrees left I'll try not to drop the drone, and then 360 degrees right. Now put the drone on its back, 360 left, and 360 right. The compass calibration should be complete after that process, and Mission Planner will ask you to reboot the autopilot, so just power it off and then power it back on again. If for any reason the compass calibration hasn't completed, don't worry, just continue to do the process. Just start from the beginning and do all the rotations again, and that should, you might have to do it several times, but that should get the compass to calibrate successfully. If the compass won't calibrate no matter what you do, then it may be that it's too close to some big electrical wires, or it's too close to the motor magnets, something like that. Try repositioning the compass so it's nice and far away from any current carrying wires, like the battery leads or the motor wires, and it's nice and far away from anything magnetic, like the magnets in the motors. And then do the whole process again, and the compass calibration should complete. Once the compass is calibrated, it's time to check your radio channels. And for this, all you need to do is make sure that your receiver is bound to your transmitter. So for Express LRS, that's really easy. You just power the receiver on and off quickly 3 times in succession to put it in binding mode. Then it will double flash its LED to indicate it's in binding mode. And then you can bind it using the bind command in the Express LRS Lua script on your radio. So that's really simple. Other radios will have different procedures. Once you've got it all correctly bound, you should see an image like this, where all of the different channels are populated with green bars, and you want to check that the center stick positions are exactly 1500 and adjust the trims on your radio to make sure that's the case. The low stick position should be less than 1000, so in my case it's 988, and the high stick position should be more than 2000. In my case it's 2011. Now it's time to set up the servo outputs, and for a simple RGCopter setup, your only servo outputs will be the motor outputs for your ESC. And you're going to want to set your servo outputs 1 to 4 to motor 1 to 4. Now, I need to make you aware that for typical 4-in-1 ESCs that don't follow the RGPilot motor layout, so if you're using an ESC that's intended for Betaflight or something like that, the correct servo number and motor number won't match. They won't be the same. So servo 1 won't be motor 1, servo 2 won't be motor 2. They'll be in a different order. We're going to address this later on during motor test, so don't worry about that now. For now, just set servo 1 motor 1, servo 2 motor 2, servo 3 motor 3, servo 4 motor 4, and then we'll change the order around later when we look at motor test. Once you've set up your servo outputs, this is also a good moment to set up your motor protocol. And this is the language that ArduPilot is going to use to communicate between your flight controller and your ESCs. You can find this setting in Mission Planner config tab, full parameter list, and you can search for MOT_PWM_type, should come right up. At this point, you need to decide whether you have a D-Shot capable ESC. Now, most smaller 4-in-1 ESCs are D-Shot capable, and in this case, you are going to set the protocol to D-Shot 300 for best compatibility. There's no benefit with ArduPilot to faster D-Shot rates like D-Shot 600, simply because ArduPilot only updates the throttle signal at a maximum of 2 kHz, and D-Shot 300 is plenty fast enough to take care of that. Faster D-Shot settings like D-Shot 600 are less reliable, they're less resilient to electrical noise, that sort of thing. So I always suggest D-Shot 300 for best compatibility. If, however, you are using ESCs that don't support D-Shot, and this is very common for large individual ESCs, particularly ESCs designed for much higher voltages, much higher power levels than the type of typical 4-in-1 ESCs that you would use for like an 8 or maybe a 10-inch drone, then if you don't have D-Shot support, you should set the motor PWM type to normal. That's going to be suitable for the vast majority of these larger ESCs. The normal protocol doesn't support bidirectional D-Shot, doesn't support D-Shot telemetry or anything like that. So you're going to need to check for your ESCs with the manufacturer's specs if the ESC supports telemetry for RPM data and temperature, things like that, via some other method, for example, UART. If it does, then you need to set that up separately. If you're using a D-Shot ESC, you can get RPM data and some other forms of ESC telemetry directly over the same signal wire you're using for motor control. And we'll talk through how to set that up. Once you've set the servo outputs, it's time to configure the serial ports. And this is going to depend on how you've wired up your flight controller. So refer back to your earlier notes to remember what number serial port you connected each of the devices to. Serial port 1, UART1, is typically set to the Mavlink 2 protocol. Leave that alone, don't touch it. That's important for connecting to the flight controller over USB, so just leave that one alone. I connected my receiver to serial port 2, UART2, and so I'm going to set the protocol to RC in. And for the RC in protocol, the speed doesn't matter. It's going to auto detect the correct baud rate. So you can just leave that as it is, 57,600. For UART3, I connected my GPS to that. So I'm going to set the protocol to GPS and I'm going to set the speed to 57,600. That's a typical speed for most GPSs. The air unit is connected to UART6. So I'm going to set the protocol to DisplayPort for most air units, and I'm going to set the speed to 115,200, which is the typical baud rate for that DisplayPort protocol with air units like the DJI O3 and O4 air units, the WalkSnail air units, stuff like that. As you may be aware, there are 3 different types of ESCs that are commonly used in drone applications. The first are PWM ESCs. These are controlled by a PWM signal. A pulse 1000 microseconds to 2000 microseconds long is sent to the ESC a certain number of times a second, 50, 100, 150 times a second. And that pulse encodes the throttle command. The longer the pulse, the higher the throttle. So if it's a 1000 microsecond pulse, that's 0% throttle. A 2000 microsecond pulse is 100% throttle. And it's an analog signal because the ESC has to time how long that pulse is, and it can take any value between 1000 and 2000 microseconds, and that corresponds to the throttle from 0 to 100%. PWM ESCs do not typically return any information back to the flight controller over the throttle signal wire. They just are listening out for that PWM signal. They take that, they calculate the throttle setting, and then that's the throttle that's applied to the motor. Some PWM ESCs have digital telemetry built into them, but that is almost always done over a separate digital telemetry wire from the ESC to the flight controller, and that is typically soldered onto the receiver pin of a UART port on the flight controller, and you actually solder all 4 ESCs to the same UART receiver pin, and they take it in turns to communicate their telemetry. The second type of ESC that you might be familiar with are D-shot ESCs. These are controlled using a bidirectional digital protocol. A digital packet is sent which encodes the throttle setting with a checksum. The ESC receives that packet, decodes it, checks it against the checksum, makes sure that everything makes sense, and then applies that throttle to the motor. This is a better protocol because you actually have some error checking in the loop, so that if there is a signal that isn't correct, that gets corrupted by some method through electronic noise or anything like that, the ESC will recognize that that packet has been corrupted and ignore the throttle signal that's contained within it. Bidirectional D-shot ESCs, so pretty much all D-shot ESCs nowadays support bidirectional D-shot. That's where the ESC can actually send packets back to the flight controller and encode information like the motor RPM, the battery voltage, and the current that's currently flowing through the ESC. All that information can be encoded into packets and sent back over the same signal wire to the flight controller. And that's really good because it allows you to get RPM data effectively for free because you've got that D-shot signal going to the ESC to give it throttle and you're getting RPM data back. The final type of ESC that you might be familiar with are drone CAN ESCs. These again use a bidirectional digital signal similar to CAN bus to control ESC throttle. The advantage of CAN is you can have multiple ESCs on the same single bus. So you only need 2 wires, 2 pins on the flight controller to control all your ESCs. Because it's a digital protocol, again, drone CAN ESCs can return RPM and other information like voltage and current over the signal wire. That can be really handy. Drone CAN ESCs are kind of the more modern type of ESC. They're not used that much in smaller drones. They're more commonly used in much bigger drones. And I think this is the way that most modern ESCs for larger UAVs are moving. So if you have drone CAN ESCs, you have D-shot ESCs, you're going to have RPM data available most likely. If you use PWM ESCs, you may not. Once the serial ports are configured, it's time to set up your ESC settings. And you can do that in the ESC calibration tab. Don't click the Calibrate ESCs button. For me, this got my flight controller stuck in a loop where it just was trying to calibrate the ESCs every time it booted up. And it doesn't work for digital ESCs because they're not interested in being calibrated. So if you've got a digital ESC, a modern 4-in-1, and you're going to be using the D-shot protocol, don't click the Calibrate ESCs button. You don't need to do it. You're going to want to set your ESC type to D-shot 300. There's no point using D-shot 600 with ArduPilot because the PID loop doesn't run fast enough to make use of D-shot 600. So D-shot 300 is absolutely fine. And you're going to want to set your output PWM minimum to 1,000, maximum to 2,000. And then the spin when armed, I would typically set that to somewhere between 5 and 10%. Probably start with maybe 5.5, 6%, see how you go. The spin minimum, that can be 10%. So that's going to be the lowest throttle setting when the drone is actually flying. And then you're going to want to set the maximum spin to 1 because you're using a D-shot ESC, which means that there's no dead zone at the top of the throttle. You just want to set that to 1.0. Once your ESCs are configured, it's time to set up flight modes. And you can do this in the Flight Modes tab. You may find that when you start to configure this, that you would like the flight modes to be controlled by a different channel on your radio. You can accomplish this by going into the Config tab, Full Parameter List, and searching for FLT mode_CH in the search bar on the right. That will help you find the flight mode setting, and you can change that to whatever channel on your radio you would like. I think by default it's channel 5, which is AUX1, but you can set it to any channel. Once you've got the correct channel configured, you can set up the flight modes. I've got it set on a 3-position switch right now. So the top position is stabilize, the middle position is altitude hold, and the bottom position is loiter. But depending on what channel on your radio you're using for flight modes, you might want to set it up differently. This is where you do that.